name is Hypatia, and I live in Alexandria. And this is the year 400 AD. In the fine tradition of teachers, I will now write this up so you know what I'm talking about. So I have just been made director of the observatory, the astronomical observatory here at the University of Alexandria. And I teach in mathematics here. I'm a professor here, as has been my father, Theon, and indeed, going back to the days of Euclid, 600 years ago, where this mathematics department was set up in Alexandria. As you know, Alexandria is a town, the delta of the River Nile, on the south shores of the Mediterranean. And we have been making astronomical observations here for many years. And I have been asked to come and give you a talk about the sorts of astronomy that I talk to my students, and the summary of where we are. What do we know? Where has Greek astronomy taken us so far? But to begin, I'd like to go back further. I'd like to go back long before the Greek Empire and think about how early peoples looked up at the sky and they saw the stars moving. They saw the stars rise and set, they saw patterns in the stars, and they made up ideas of what they were. They thought they were mythical beasts, mythical beings, all sorts of characters in the sky, and they told stories about how they came to be and what they were doing as they rode through the sky, and the relationships between them. They also noticed there was a pattern, there was a rhythm to the sky. The sun would rise and set, the stars would rise and set, the moon would go through changes of phase. It would look different at different times every month. And so this pattern of the sky was very important to the peoples as they looked at the sky. But their view of the universe was based entirely in what their imagination could see. Now, a civilization grew up in Babylonia, which grew up between the fertile valley of the Tigris and Euphrates rivers, and that society, the Babylonian society, began to not just look and build up stories, but they began to count and to measure. And they measured the time, how many days it took the moon to go through its cycles of phases. They measured how long it took their favorite star, say the dog star, Sirius, would first be seen at twilight on the horizon on a certain day of the year, and so they counted the number of days it took till it came back. And they said that's about 360 days. They later realized that it was more like 365, but that was kind of inconvenient, so they fudged it. But they knew they could develop a calendar based on the cycle of the moon, the cycle of the sun. And this was very important. It allowed them to do a variety of things. They could predict when the floods were going to occur. Very important if you're an agricultural community. So the astronomers had power. Furthermore, they could predict eclipses. And as you know, eclipses are really scary things because the sun goes out and it gets dark. And so astronomers developed power in their society because of their ability to predict what was going to happen. Now, after but their view of the universe was entirely based on the idea that there was a mythology. Their cosmology, their view of the universe was based on some idea of some stories that they made up. For example, they didn't know how the universe was constructed, but they built ideas. For example, they thought, well, when the sun rises in the east, sets in the west, what happens then? Well, they thought the Earth was flat. So where on earth could the sun go when it set? So they said, okay, somebody puts it in a boat, puts it in a canal. It's very hot. They thought they had to be carefully carried around to the east where it could rise and set again. So their view of the construction of the universe was very primitive. The big change happened with the Greek Empire because the Greeks started to develop two tools that were key. One was that of mathematics and philosophy, and the other one was that of measurement. And so let me give you some examples. Let's start off with our friend Pythagoras. Okay, so you probably know the famous theorem that Pythagoras developed, and he was around 500 BC. Somebody tell me Pythagoras' famous theorem, or what is it about? Any ideas? About triangles? Yes? Okay, so let's make not just any old triangle, but a right angle triangle. So we have a right angle here. So we can label the sides. What do we call this long one? Hypotenuse. Let's call it the height. What about this one? Let's label this angle with a theta. So what's this one called? It's the one that's adjacent or next to the angle. So let's call that adjacent. Sometimes you use letters for these, but let's use these names. And then the one that's opposite is called opposite. Okay. So Pythagoras' theorem developed a relationship between these sides. What was the relationship? Excellent. The hypotenuse squared is equal to the adjacent squared plus the opposite squared. So these distances have a fixed relationship. And this has been used for millennia by construction workers building houses. And is still used today. So let us take this one step further. We can use the relationship of this angle to these and say that that the tangent of this angle is equal to opposite over adjacent. Now, you may say, well, what's this got to do with astronomy? But it was a useful factor because we want to be able to describe what's going on with the stars. So, may I have an assistant to come and help me in a little experiment, a demonstration? It's very harmless. Great, thank you. You just come up here and stand like this and hold. That's it. Okay. So what we're going to do is we're going to measure the location of the star, and I'm afraid I'm going to have to ask you to hold it up high. Okay, so let's imagine that there is a star in the sky, and I'm going to draw it here on the board, on the door there, and imagine that we wait to measure and categorize that star. What we do is I ask my assistant to move and stand a certain distance away, move your other arm, and move it up. Keep the other arm still. Move it up the string. The other. That's it. Move it up, 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 up. Wait a minute. I've got to stand here. Up, 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 up. Stop. Okay. So we quickly, before his arm gets too tired, measure number of units. Scribe. Write it down, please. 1 3/8. And then we go out and measure 1, 2, 3, 4. Thank you. Thank my assistant, please. So now we're able to say that for this star, we can write down in our star catalog that our friend star A on a certain date, the date when it rose for the first time, appeared at twilight, crossed the meridian, the highest point in the sky. It had a certain angle. We measured the opposite and the adjacent angles of the triangle, so we can label, we can measure the star and now categorize it. And so over a period of time, collect and describe and measure the stars and describe what they are in the sky. And this became an important development. So we then had a cosmology, the beginnings of a cosmology that was based on measurement. Because what we're doing here is developing an idea of how to explain what's going on. The first thing that you do to explain why the stars rise in the east and south. The west has to do with describing how it's laid out, how it came to be. Now, let's move on to 350 BC. The famous philosopher Aristotle, who was very interested in the idea that that the Earth was round. It seemed obvious to many people, but other people insisted that it should be flat. Now, why do you think, if you're a Greek person living, say, on the shores of Greece, beautiful fish that gets caught every day, sunsets, beaches, you have a great time, but you notice something that allows you to decide that the Earth had to be round? What might you see when you look out to sea? Yes, chap in red there.
Yeah, it looks like it curves.
Looks like it curves, yes. How might you test person in blue?
When someone sails a boat outward, eventually will disappear.
Right. So you see boats go out to sea and they disappear. And they don't just get smaller and smaller and smaller, which you would expect if the Earth were flat. They begin, the bottom of the boat disappears, and then eventually the top of the boat disappears. So Aristotle argued that indeed the Earth was round. He wasn't the first to notice this, but probably he was the first to write it down. And, you know, in the true tradition of academia, what you get credit for is what you write down and publish. So he noticed that the Earth was round, and he began to think about the moon. Is the moon round, or is it just a disk? And so he began to construct an experiment to try and convince himself whether it was round or flat. And so he built a model, a physical model of what he thought was going on. So let's try this here. Let's build a model that illustrates the concept of whether or not the moon is round. So let me make ourselves a sun. Maybe lots of light. And if I might ask my assistant to reduce the ambient illumination. And we want to think about whether or not our moon is indeed round or flat. And so we can say, what if it's a disk? Okay? And we can say, okay, so if we are here and we look at the illumination on the disk as the sun shines on it, and we say, wait a minute, this doesn't make sense. This isn't how the moon looks, the phases of the moon. It seems to be turned on, turned off, immediately turned on. Very strange. That isn't how the moon looks. But if we take a ball, a sphere, and we say, okay, now let's look with the sun illuminating the ball, and our eyes being us on the Earth looking at the moon, you can begin to see that it goes a little bit. There's a full moon here, my head away, and then it comes around, and we have half light, half dark, and so on. We can see it go through phases. Okay, so this is very important because it tells us that the moon is round. Let me put the light back on the moon. The other thing that he did was to think about these eclipses and think about the shadows. It was realized that the lunar eclipse was when the moon moves through the shadow of the Earth, and that a solar eclipse occurs when some spot on the Earth, the moon covers up the sun, and so its shadow is on the Earth. Okay, we can turn the lights back on, and I will blow these out. So what this was able to do was to help us develop a sense of the construction of the the Sun-Earth-Moon system. And this was really key for working out what's going on. The next guy who came along, in particular Aristarchus, look at my notes to remember his dates. He's 250 BC. Worked very hard on this issue of the Sun-Earth-Moon relations. And so what the first thing he did was he said, okay, if we have the Sun here and we have the Earth here, we know that at a time of eclipse, the Moon gets exactly in the way of the Sun. And so we know that the angular size of the Moon is the same as the angular size of the Sun. And so if the Sun's further away, it must be bigger than the Moon. Okay? But he had done the same experiments that Aristotle did with candles and balls and so on, and tried to work things out, and realized that when you look at the shadow of the Earth on the solar rays coming from the Sun here, a long way away, the Moon is much smaller, and so it goes through. You can see that the size, let me just make that smaller, the size of the Moon has to be much smaller than that of the Earth. In fact, he realized that the Moon was roughly a quarter the size of the Earth. Now, how this exactly was derived requires a fair amount of geometry. But he realized that if you look on the Earth, where do you see these eclipses? These eclipses are not observed everywhere at once. The Greek Empire being large, they realized, because runners would come back and report to the main administration in Athens and say, oh, we didn't see an eclipse, we only saw a partial eclipse. And so they realized that different places of the Earth did not see the whole eclipse, but just part of the eclipse, so that the area of the Moon's shadow on the Earth had to be a lot smaller than the shadow of the Earth on the Moon. Now, he took this a step further and made a further, very clever geometrical argument. What he did was to draw a diagram that looks like this. So let me do this carefully. Again, it's right triangles, our friends. We have the Sun over here. And then we have a Moon. And I'm not going to make it tiny because I want you to see it's half illuminated, dark on one side, light on the other, obviously facing the Sun. And then we have the Earth somewhere here, where we're looking at the Moon. Now, you know that if the Moon is half illuminated, then this part here must be a right angle, okay? Now, very cleverly, the observer looking at the Sun and looking at the Moon could work out using, actually let me draw this a little more better this way. The difference between the this angle, that's right angle to the Moon, and the angle of the Sun, using bits of string and tape measures and so on, and realized that this angle is only about 3 degrees. This is what he measured. Okay. So perhaps you can work out, using this, the distance to the Sun, okay, relative to the distance of the Moon. So we can say E, Earth, Moon distance, Sun distance, and so we can use our trigonometry again. Sorry, Moon, the This is the Earth-Sun distance. This is the Earth-Sun distance. Thank you. That the Earth-Moon distance divided by the Earth-Sun distance, there's a trigonometric relationship between those two. Can somebody tell me what it is in relation to this angle theta? What is it? It's the sine. In this case, the sine of 3 degrees, which is about 1/20. Okay? And so Aristarchus concluded that because of the eclipses them having equal angles, that meant that the sun had to be 20 times bigger and 20 times farther away than the moon. Okay? And so he concluded the sun is 20 times bigger than the moon, and that the Earth is only 4 times the size of the moon. Then he concluded that the sun is much bigger than the Earth, which is also bigger than the moon. Now, this angle, you can imagine, is very difficult to measure. It's a small angle. In reality, we now know this was a measurement made back in 250 BC. In 400 AD, we can do it a little better. And we know that that number is larger. In fact, it's more like 1/400. Okay, but the point is this. Aristarchus was able to make a fundamental leap in our view of the construction of the universe by making these measurements and concluding the sun is bigger than the Earth and the moon. Now he took an extra step further and said, okay, if the sun is so much bigger, then the sun, must be the center of the universe, not the Earth, the center of the universe. So back in 250 BC, he wrote down these arguments. We'll come back to this issue in a second. Okay. Now, the next measurement that's worth thinking about, important one in our construction of our cosmology, our construction of the universe, is by a guy whose name I have to think very carefully to spell, Eratosthenes. And he was 200 dates. 200. Okay. And what he did was to say, he worked here in the observatory in Alexandria, and he was involved with the administration of the empire, and he knew that on a certain day of the year, it was reported in a town, Cyrene, south of Alexandria, that the sun would come straight overhead and go straight down a well. So it was vertical down. And he thought, aha, let me think about this. And he was able to use this to make a very important measurement. Okay, so here we have the Earth. We know it's round because we see those boats going over the edge. Let me draw this carefully. So we have a well. So the sunlight comes down, straight down the well, okay? At this place, Syene. Now, Alexandria, which is a little further north, we know that the sun, on that same day, comes from the same place, does not come straight down, but makes an angle. So we can take our plumb bob, which we know goes straight down. We can measure where the sun is, and we can say, okay, what is this angle between the sun and straight down? And what he measured was that this angle was 7 degrees. Okay? So now we can use our geometry of the Earth. We know that the distance between these two places, d, is about 5,000 stadia is the unit that is used, or 5,000 size of a stadium, a standard unit that we use here in Greece, and the Greek Empire, Alexandria being part of the empire. We now know that 2 pi of the radius of this Earth, okay, is the circumference and we know that the ratio d over 2 pi r is equal to 7 degrees divided by what? 360, the number of degrees in a complete circle. Okay? So this fraction, this wedge here, is the same fraction in terms of d over the circumference is that 7 degrees is to 360. And so that we know that the radius, therefore, and this is about a number of 1 over 50, the radius has to be, the circumference, 2 pi r, is roughly 50 times our distance d. Okay? And so this means that just by making these measurements between 2 towns of the angle of the sun with the sky, and then multiplying that by the angle the sun makes, you're able to work out the size of the Earth. So this is the absolute scale. This is the size of Earth in absolute units. And if you know the size of the Earth in absolute units, you can use this relationship to get the moon in absolute units and the sun in absolute units, and so on. Okay? So in some ways, this is a way in which we bootstrap our way up, developing a sense of how the universe is constructed based on measurements, based on ideas of how the world works, and testing those ideas by making measurements. Yes?
I don't understand how he knew when to make the measurement of the other places. Like, how did he know that the sun was directly above the well?
Right. Okay, so this requires some level of communication. Okay? And so there has to be communication between the town of Syene and the town of Alexandria, right? Now, it's a day or so camel ride, not that far away. Okay? And furthermore, these ideas, people have been looking down the well for years and years. They kind of knew that it was going to happen. They also knew, the astronomers, the local astronomers told them what day of the year it was, right? Because they knew what star was just, it was 3 days after the first day that Sirius was first observed on twilight, right? Sounds somewhat clumsy, but they had developed a calendar based on the idea of the stars. And so then on the same day, okay, so 5 days or whatever it is, 3 days after Sirius is rising first time at twilight, we will go measure the sun and make this angle on the same day. Okay? And it was a little crude, it was a little rough, but actually a very good measurement. Okay? Yeah, you do it at high noon, obviously. You want to do it when the sun's right overhead. Now remember, the sun is not always overhead everywhere. Okay? So this is in a location on the Earth where the sun is directly overhead at noon on that day. Yes?
Didn't the Egyptians before then do something similar with obelisks?
With obelisks.
And keeping logs, in different portions of the Nile Valley? One in Cairo and the other one was like the most part, or in Egypt.
Whether or not they actually were able to make a conclusion about the size of the Earth, I don't know. I'd be interested in hearing more about that and the date of when they were able to do this. But the recorded measurement, Eratosthenes gets the credit for that, even though maybe similar thoughts have been given to other people.
The Egyptians were not even using the Arabic form of math at the time. They were using a different set of numbers altogether.
Right. But were they able to make this conclusion of the absolute size of the Earth?
No, I think it was more of an observation. And this was like 15 years ago. I was watching Carl Sagan's
Okay.
series, cosmos stuff. So we
Okay,
mentioned it there.
so let's talk about this afterwards. Okay, I'm very interested in it. Okay, so this was an important development. We knew the Earth was round, we knew how big it was, and from that we could construct our idea of the cosmos and how the universe, indeed the local universe, just the Earth, Sun, and Moon system, is constructed. But what's key is we want to know whether or not the Earth is moving. Because if Aristarchus is correct, and that because the Sun is the largest object that we know, much larger than the Earth, then he argues that the Sun must be the center of the universe and the Earth must be moving around the Sun. Then if the Earth is moving, we should see the stars move. Okay? Just as I move in my orbit around our Sun here, the candles, I see you move relative to each other. Whereas if I stay fixed, you remain fixed like stars. Okay? Then there is a question about, we can measure this. Okay? So this is a way in which we have a hypothesis that we can test. A hypothesis that the Sun's the center and the Earth moves around. Let's test that by making measurements. And the person who made the best measurements, the first real astronomer, is a guy, I have to get rid of Pythagoras here, called Hypatia. And I think he's 130 BC. And he catalogued the stars in the sky using that very technique of the plumb bob and measuring it. So a little bit more sophisticated, but he measured on the order of 850 stars. So that's most of the stars that you can sort of see with your naked eye easily in the dark site. He catalogued them, measured their location, their date fairly precisely. And he was able to notice that there is no parallax that he could measure. So parallax is this business of if you're moving, then things appear to move relative to the stars. So that if the Sun was at the center and the Earth was moving around, when you look at a bunch of stars over here, say this star here, when you're over here, at a different time of the year, you would see it over here, then it should move relative to the background stars. He was not able to measure that movement. And so he concludes that Earth is fixed. He also made various other things. He was able to measure precession. So he was accurate. Now somebody tell me what procession is. We talked about this before. I believe you know what procession is. There's a less sophisticated word called
Wobble.
Okay, what is the wobble of procession? Somebody tell me what it is. Any ideas? What does it describe? What's wobbling?
Like the axis of the Earth
Yep.
doesn't stay exactly
Yep.
the same.
It wobbles.
There's a precession.
Right, okay, good. So the axis of the Earth is spinning like a top, but it doesn't stay fixed, always pointing to Polaris. It wobbles around over a long period of time. This is equals the wobble of Earth's spin axis, and this happens on the order of 26,000 years. So you can see that he was not a sloppy astronomer. He didn't not measure parallax because he was sloppy. Okay? He's not able to measure it. Okay. So, the last astronomer of import that we need to discuss, again an astronomer from the University of Alexandria, here, and on whom I have written several books and treatises, in fact a textbook on Greek astronomy and his view of where we are in our cosmology of construction of the cosmology is Ptolemy. Now there are in fact many Ptolemies, but the one we're talking about, 140 AD, and the books that he wrote describing the layout of the universe is the Almagest, of which there are about 12 volumes. This is not a small book, a very important description of the stars and the sun and moon and their motions. But what intrigued Ptolemy was to think about the planets. Now, the word planet comes from wanderer in Greek, and if you look at the planets in the sky, you notice that there are some times of the year when they appear, instead of keeping going in the same direction, to make a loop-de-loop. Okay, they make a loop in the sky. This is called retrograde motion. They go backwards. And the way in which Ptolemy described this, he was able to construct a mathematical way in which this could happen, but still keep the Earth at the center of the universe, right? If Hipparchus, the best astronomer ever, is not able to measure parallax, the Earth must be fixed. So we have to construct a cosmology based on that. And so he said, we have the Earth there, the sun going around the Earth, and then we have planets which go around in their own circular orbits. Okay? Because we want to follow the Plato's philosophy that everything is perfect in the universe. It's nice circles, everything's circular. And so if you do this, what happens is the planets appear to make this loop-de-loop motion in the sky known as epicycles. Okay? And so this is a way to explain the retrograde motion of the planets. And indeed, by adjusting the size of this circle and adjusting the size and the rates and so on and so forth, you can come up with a way of describing this loop-de-loop motion very accurately. And therefore able to predict the motion of the planets in the sky and what's going to happen next and where everything is. And so the Almagest is a very important piece of paper, 12 volumes of endless descriptions that I have tried to simplify. But we're at a point where we now have a description of the motions of the planets around the Earth. So what is the heritage that we're left with at the time of the Greek, where we are now at 400 AD?
Well, we're certain that the Earth is the center of the universe, and that's it.
We're certain that the Earth is the center of the universe, but we've done much more than that. We've got a measurements that tell us the Earth is round. We know what size it is in absolute units. We know that the moon is round. We know what size it is in absolute units. We know the size of the sun and how far away it is pretty well. We have a cosmology that's based on measurements, and indeed, what we have now is a science, a way of constructing a view of the world around us but is indeed based on these measurements and ideas of the physical construction. We're not building stories in the sky of, the bear chasing the lady whose head was cut off and, all this sort of stuff. We're using mathematics to predict eclipses, to predict the time of the year when floods will occur, to predict when the moon will go through certain phases, predict when the Venus will be in certain places in the sky, and so on. So we have what you could call a way of constructing knowledge, epistemology, to use a fancy word, that is based on, we have a theory that allows us to develop a hypothesis. We can then use this hypothesis to make a prediction, which we then test with measurement. And then we may have to adjust our theory, okay? Maybe the measurements tell us the theory doesn't work. In the case of Aristarchus, we have made measurements that tell us, measurements made by Hypatia told us that the idea of Aristarchus, that the Earth was the center, does not match up with measurements, so we have to adjust our theory and so on. Okay? And so this is the heritage of the Greek academic world. The Greek civilization has produced a description of not just astronomy that's based on mathematics and measurement, but also the whole of our world around us and a different way of looking at the universe. So thank you very much indeed.